We've already talked about how we can parametrize lines in space. Now we can generalize that to actually parametrizing any curve in space. So what I have here is, first, let's imagine we parametrize a three-dimensional point in space with functions for the x, y, and z components. We're going to let the x, y, and z components be defined by f of t, g of t, and h of t. So this blue point here, I'm just going to move it along and imagine as we change t, which is usually for time, that point is going to change with respect to the function. So in this case, f of t is t, then you have sine of t, cosine of t. This curve is basically going to draw out a spiral in space. This is the usual form for a spiral or a coil, which shows up a lot in nature. It's important to note that the curve itself and the point are two separate things. This blue point, the dot, it's just a single point in space, and the actual curve is the set of all points between an initial time and the current time that we have for this parametrized point. One application of parametrizing curves in space is that it can actually help us describe intersections between surfaces in space. So let's say we're given this function z is equal to x squared times y. This is what that looks like. And y squared plus x squared equals 4. In the plane, there's just a circle centered at the origin with radius 2. And in 3D, it's just, you're going to take that circle and move it along the entire z-axis. So it's going to be a cylinder, a circular cylinder. So the objective is to find some way to describe the intersection between this cylinder and our function. Now, the first thing to do you could try to isolate x squared here, and it'd be equal to 4 minus y squared, and then substitute it back into here, and you'd eventually arrive at a system of equations that would give you the equation of the surface. But I want to introduce a different way to do it, and that's going to be using a different parameter and have x, y, and z each be functions of that parameter. This helps because sometimes we run into functions of x, y, and z that aren't exactly defined for all values. So this parameter, one, it helps us get rid of that, and also it's kind of easier representations of x, y, and z for these curves. I'm not going to go too much in depth into how I arrived at these equations and solved for the parametric representation of our intersection, but I'm going to uncheck this, and pretty much this curve does give us all points where x, y, and z satisfy this function as well as our cylinder. So I'm going to uncheck the cylinder and show that, yeah, these points all do lie in the function, and they are all constrained to the cylinder as well. So that's one application of base curves and using parameters to describe curves in space. Not only does this apply to using a parameter for a point, but we can actually use a single parameter and get out a vector. So what these are called are vector valued function, and basically it's a function that takes in a single real number and it outputs a vector with any number of dimensions. So it could be one-dimensional, two-dimensional, three-dimensional. Today we're going to talk about three-dimensional. So our vector functions are going to take in one parameter t and going to give a vector with 3 components with respect to t. To better explain that, I'm simply going to draw a vector from the origin to our current point on the space curve. And if you remember, this is basically a position vector representing our point on the line. The vector and the point itself, it pretty much represent the same thing. It's just our single point in space. So as you can see here, whenever we change t, that vector starting from the origin is just going to end up exactly where our point is. And that's the essence of a vector valued function. It takes in, or any number of inputs actually, and outputs a vector whose components are functions of our input. The thing is, in calculus, we deal with change, and when we deal with functions, we want to talk about derivatives and integrals. That's the essence of calculus itself. It measures change. So what I'm going to introduce is a tangent vector, and this tangent vector to help you better understand, it's pretty much the vector that's tangent to the path we're going in. It's going to be tangent to this curve. You can better see or understand that this purple vector, which is our tangent vector, is pointing exactly where the instantaneous change is happening from where we currently are on the curve. First, let's start with taking the derivative of our vector valued function. The same thing in single variable calculus, we're going to start with the limit definition of a derivative. And so if we take our function and we have our change in time, delta t, the derivative is equal to the limit as that time approaches 0 of the difference quotient between our second position and our first position. Algebraically, we just write that as r of t plus delta t minus r of t divided by delta t, taking the limit as this divisor approaches 0. That's going to be our derivative of our vector valued function. Again, our vector valued function is just a vector with components that are also functions of our input itself. So I'm just going to expand what's written here and give that to each x, y, and z component. And from this, just applying the limit to each component, you'll find that the derivative of our function is actually just a vector with the derivatives of each component function as its components. It's pretty straightforward. Just given this is our vector, we just take the derivative of each component, and that's the general derivative of a vector valued function. However, algebraically, all this is telling us is that given our function, our derivative is another vector with components, and components are it's just a vector with numbers in it, and we want to know what these numbers represent, or what this vector with values represents. To help show what it actually represents, I've drawn a zoomed in picture of a space curve with position vectors. So imagine our first vector, r of t1, being here, the black vector, and then our second vector, which is r of t1 plus our change in time. So this red point is pretty much the point given if we started from our first time plus the change in time, whatever that change in time is. And I've written the respective components in terms of t1 and t1 plus the change in time. So given these two vectors, I'm going to draw a secant vector, with just the vector between those two vectors, or the 2 points that those vectors point to. If we start from the origin and then go our first vector and then add the secant vector, we end up at our second vector with the addition of the change in time. So to write that algebraically, I'm just saying r of t1 plus vector s, our secant vector, is equal to r of t1 plus delta t. And I'm going to rearrange that in terms of our secant vector. And that's just saying our secant vector is equal to our second vector minus our initial vector. What's convenient is that this right side, r, the second r, minus the first r, it actually shows up in the numerator of our difference quotient here. So what I'm going to do is I'm basically going to recreate the difference quotient from this. The first thing I'm going to do is divide by delta t, and then take the limit as delta t approaches 0. So again, this is an equation, so I'm going to do it to both sides. And we have the limit as delta t approaches 0 of our secant vector divided by the scalar delta t is equal to the limit of our difference quotient. And we know that this limit is eventually going to be the derivative of our vector function. So we know that this limit of our secant vector is going to be equal to the derivative of our function. So I want to explain what the limit of our secant actually means. So again, in single variable calculus, we took the secant between 2 points, and we observed how as that delta t becomes 0 itself, this secant line eventually becomes the tangent line at our original point, and the slope of that tangent line is the derivative of the function at that point. So that means as our delta t approaches 0 of our secant line, divided by delta t is going to be our tangent vector, or the vector that's pointing in the direction of instantaneous motion. Moving back to Desmos, I'm going to include the secant vector to help better elucidate what's actually going on. Imagine our red vector is our second point, or the point we have after we've moved a change in time, our delta t. So let d equal our delta t, and just notice how as d approaches 0, our second point, and it becomes the initial point. And our purple vector along this gray line, don't worry about why it's not the full length. We'll talk about that next video. But that purple vector is the secant, or it's in the direction of the secant line between our 2 points. And again, as that distance becomes 0, our secant line eventually becomes the tangent vector. I'm just going to change t, and yeah. So our tangent vector is tangent to the curve and points in the exact motion we're going. To help better show that, let's just look at it in one plane, the YZ plane. This is a circle, and we know that this tangent is going to be, well, tangent to the circle. And that's exactly what's happening. We see that it maintains that 90-degree angle throughout the whole thing. We can also go in the XZ plane. This is a sine wave. Our tangent vector is still tangent to our curve, no matter which way we look at it. That just goes to show how the derivative of our function is just the derivative with each component. So that was a quick introduction to space curves, vector functions, and the tangent vector. In next video, we're going to go more in depth into what the magnitudes of the tangent vector actually represent and how it relates to things such as velocity of a moving particle in space and its acceleration. Also, how we can describe how curves curve themselves. So curvature, and yeah.